Okay, imagine this. You're trying to maybe thread a needle or just read a quick text on your phone, but everything's, it's just blurry, hazy.
Mm.
Or maybe colors just don't seem as bright anymore. That's reality for millions of people dealing with cataracts.
Yeah, and it's really more than just, an annoyance. Cataracts, that clouding of the eye's natural lens we're talking about, they really mess with your vision. Clarity goes down, contrast sensitivity.
Right.
It's actually one of the biggest causes of preventable blindness globally. We're talking nearly 95 million people affected.
Wow. But the good news is there's a really effective solution, right? Cataract surgery.
Exactly. It's become a standard procedure. You basically swap out that cloudy natural lens for an artificial one, an intraocular lens or IOL.
And it's usually pretty quick, like an outpatient thing.
Yeah, typically. They place a tiny foldable IOL inside the eye in what's called the capsular bag. Very successful surgery, generally.
Okay. But the surgery is one thing.
Hmm.
The lens itself, the IOL, that's got to be key.
Absolutely. How well these IOLs work really boils down to two main things: the materials they're made of and their actual structure or design.
And that's what we're digging into today, isn't it?
That's the plan. We want to help you understand the really crucial factors that make an IOL effective and also take a peek at where the technology is heading. It's pretty exciting stuff.
Cool. And we're basing this on what kind of source material?
We're drawing from a recent scientific review article. It basically pulls together a whole bunch of existing research on IOLs.
Got it. So a good overview of the current state of play. Okay, let's unpack it. You said material and structure are the keys. What about the material itself? What are the critical things they look for?
Well, the review points to several things. First, how the lens interacts with light. That's the optical properties.
Makes sense.
Then how well it gets along with the eye tissue, without causing problems. That's biocompatibility.
Right. Don't want the body rejecting it.
Exactly. Then, obviously, transparency is vital, needs to be clear. And finally, biomechanics, sort of the physical characteristics, how it holds up inside the eye.
Okay, so optical quality, body-friendly, clear, and physically stable. Seems logical. And the structure, the design of the IOL, how does that play in?
The structural design is super important for getting a good mechanical fit, both during the surgery and afterwards. It kind of helps guide the surgeon, too. And crucially, the shape of the lens surfaces its geometry combined with its refractive index, which is basically how much it bends light.
Yeah.
That's what defines the lens focusing power. It's prescription, essentially.
Right, getting that light focused perfectly on the retina at the back of the eye.
Mm-hmm.
Okay, so this review mentions two key ways they actually measure how well these IOLs are doing their job. What are those?
The two big ones, the sort of standard metrics, are optical transmittance and optical scattering.
Optical transmittance.
Yeah.
That sounds like how much light actually makes it through the lens.
Precisely. It's the percentage of light that passes through the IOL and reaches the retina, where vision actually happens. And it's not just one number. It actually depends on the wavelength, the color of the light.
Right.
A healthy human lens, for example, is incredibly good at letting visible light through. The review cites research showing it transmits something like 80% of light way down at 360 nanometers, and that quickly jumps up to around 90% in the main part of the visible spectrum, between 450 and 540 nanometers, and it stays high even into the near infrared.
Wow, 90%. That's really efficient. I can see how the clouding from cataracts would just tank that number.
Totally. So when you put in an IOL, you need that artificial material to also let as much light through as possible, or at least transmit light in a very specific, intended way.
Right. So the review looked at different IOL materials and how they stacked up on transmittance.
It did, yeah. It summarized findings from various studies.
Yes. So what did they find? This is where it gets interesting.
Well, looking at the data compiled in the review, PMMA, which is polymethacrylate, it's one of the older, more established materials.
Okay.
It generally seems to have really high transparency. One study mentioned found transmittance up around 99.7%.
Perfect transmission, almost nothing blocked. What about some of the maybe newer materials?
So there's work on PMMA copolymers, like adding something called POSS, polyhedral oligomeric sesquioxane. Bit of a mouthful.
Oh, yeah.
Some research suggests adding POSS can actually increase transmittance compared to just standard PMMA. And maybe offer other perks like better surface properties, maybe better biocompatibility.
Sounds promising.
It does, but the review also cautions that there isn't a lot of long-term data on these yet, and there
Yeah.
might be some, technical challenges to getting them into widespread use.
Okay, so potential, but maybe needs more time. What about the acrylics and silicone lenses? I think those are pretty common now, right?
Boy. Very common. For hydrophobic acrylics, the water-repelling kind, the transmittance seemed to vary a bit between the studies cited. Some showed really high numbers, others were a bit lower.
Okay.
Hydrophilic acrylics, the water-loving ones, generally showed high transmittance, sometimes up there close to PMMA levels.
Right.
And silicone IOLs also had good transmittance, though maybe slightly lower than PMMA in some comparisons mentioned. But again, these are broad categories. Specific models within each material type can differ.
Gotcha. And those yellow-tinted IOLs, the blue light filtering ones.
Ah, yes. Well, as you'd expect, they showed a definite drop in transmittance, specifically in the blue light range, around 450 nanometers.
Which is the point, I guess.
Exactly, that's their job. But their transmittance for longer wavelengths, like green and red light, remained high.
Makes sense. Filter the blue, let the rest through. Now, you mentioned the review highlighted an issue with how overall transmittance is reported. Something about standardization.
Yeah, that's a really important point they raised. There's no single agreed upon way to report overall transmittance. Some studies give you numbers at specific wavelengths, others calculate an average.
But the average might hide important details.
Precisely. How do you calculate that average? Is it weighted? Over what range? It often isn't clear, or it varies. The review really stresses that a single average number isn't enough. You need to see the whole curve, how transmittance changes across the full spectrum, ideally including the near-infrared, which is important for some diagnostic eye imaging.
Right, because two lenses could have the same average but behave very differently at specific colors of light.
Exactly. Standardized reporting showing the full curve would make comparing IOLs much easier and more meaningful.
Yeah, that seems crucial. Okay, so that's transmittance, how much light gets through. What was the other key property? Optical scattering.
Optical scattering, yeah.
What is that exactly, and why does it matter for IOLs?
Scattering is basically light getting bounced around or redirected as it passes through the lens material. Think of light hitting fog, it gets scattered.
Okay, so less scattering is better for clear vision.
Definitely. Too much scattering reduces the sharpness, the contrast. It can make things look hazy or washed out. In fact, the cloudiness of a natural cataract is mostly due to increased scattering from changes in the lens proteins and structure.
Ah, I see. So for an artificial lens, an IOL, the aim is to keep scattering super low.
That's the goal. You want minimal scattering from the lens material itself, and you also want to prevent things after implantation that could increase scattering over time.
Like what? What could happen after surgery?
Well, things like biofouling, basically biological stuff building up on the lens surface,
Yeah.
or changes within the lens material itself. The review looked at scattering measurements using a technique called Scheimpflug imaging.
Scheimpflug. Okay.
Yeah, it lets them measure scattered light very precisely, often reported in CCT units. They can measure scattering from the front surface, the back surface, or from inside the lens material itself.
And what did they find when they looked at scattering in different lenses and situations?
One really key thing is how much water content affects scattering. It can change a lot depending on whether the lens is dry, just wet, or fully hydrated, saturated with fluid. This ties into things called glistening and nanoglistening.
Glistening. Like sparkles.
Sort of, yeah. They're basically tiny pockets of fluid, microvacuoles, that form within the lens material and scatter light. Glistening involves larger vacuoles, more noticeable scattering. Nanoglistening involves much smaller ones, can make the whole lens look a bit whitish.
And does the material type affect this?
It seems to. Glistening, for instance, is known to be more common in some hydrophobic acrylic materials, the ones that don't absorb much water.
Interesting. So the material itself and how it interacts with the eye's fluid environment over time really impacts scattering.
Absolutely. They also found differences between brand new lenses, inventory, and lenses taken from cadaver eyes. The cadaver lenses generally had higher scattering.
Suggesting changes happen even after implantation. Maybe subclinical stuff.
Potentially, yes. And explanted lenses, ones removed surgically due to issues, often show even higher scattering. It highlights that things can change inside the eye, sometimes subtly, affecting optical quality.
Right. So comparing the base materials again, how did they stack up on scattering performance?
Based on the studies compiled, PMMA generally came out looking pretty good. It tended to have the lowest scattering in several comparisons.
The old standard holds up well there.
It seems so. Hydrophobic acrylics, while known for potential glistening and showing higher scattering in some studies, didn't always lead to significantly worse optical performance in tests, especially when properly hydrated. But it's definitely a factor to consider.
Okay, so we've covered the current materials, transmittance, scattering, the nuts and bolts. But the review also looks ahead, right, to things like 3D printing for IOLs.
Yes, additive manufacturing. That's where things get really futuristic and potentially transformative.
How so? What's the big deal with 3D printing lenses?
The huge potential is for customization. Truly personalized optics. Imagine an IOL designed not just for a general population, but specifically tailored to the unique optical fingerprint of your eye.
Wow, okay. That would be a game changer.
Totally. And it doesn't stop there. There's talk of 4D printing, making implants that can change or respond over time, maybe releasing medication directly into the eye, for instance. A drug-eluting IOL.
Seriously, a lens that doubles as a drug delivery system. That sounds like science fiction.
It does, but it's being explored. Another really fascinating possibility is mimicking the natural lens's gradient refractive index.
Gradient index, what's that?
Our own natural lens isn't uniform. Its focusing power actually changes gradually from the center outwards. It's strongest in the middle, weakest at the edge.
Okay, why?
This gradient helps to counteract some of the optical imperfections or aberrations from the cornea, the front surface of the eye. It helps give us sharper vision.
Ah, clever design by nature.
Indeed. And researchers have already used 3D printing techniques to create experimental lenses that do have this kind of gradient index. If you could combine that with the right biocompatible materials,
You could get IOLs that provide even more natural, sharper vision than what we have now.
that's the hope. Potentially correcting for subtle imperfections in a way that standard uniform lenses can't. Highly personalized vision correction.
So where are we with actually 3D printing IOLs right now? What's the current research showing?
It's still quite early days, relatively speaking. A lot of the focus is on figuring out the best materials and perfecting the printing methods. Hydrogels are looking promising.
Why hydrogels?
Because they're generally biocompatible, they like water, which is good for being in the eye, they can be optically clear, and they have decent mechanical properties. One group reported printing a hydrogel IOL that seemed biologically compatible.
Any other materials being tried?
PMMA has been printed, though one study noted the transmittance wasn't quite as good as conventional PMMA IOLs yet. Another group prototyped an IOL using a type of photopolymerizable resin, a light curable plastic, and measured its transmittance but didn't report on scattering.
So it sounds like progress is being made, but maybe the focus hasn't fully shifted to matching the optical performance of current lenses yet.
That's a key point the review makes. A lot of the current 3D printing work is understandably focused on just making the lens and checking biocompatibility, but there's a lack of thorough examination of those standard optical properties we talked about, transmittance across the spectrum, and scattering.
Right. Need to know if they actually work well as lenses.
Exactly. And also how they'll hold up long-term inside the eye. The review really hammers home the need for applying those standard optical tests, transmittance, and scattering to these new 3D printed IOLs, especially after simulating aging or long-term use.
So we can make fair comparisons.
Precisely. We need that standardized data to see if these potentially revolutionary techniques can actually deliver on their promise and meet or exceed the performance of current IOLs.
Makes total sense. You need the benchmarks.
Yeah.
Okay, well, this has been incredibly insightful. A real deep dive, true to form.
Glad it was useful.
So just to quickly recap the main points for everyone listening. The material an IOL is made from and its physical design are absolutely critical.
Yep.
We evaluate them mainly using optical transmittance, how much light gets through, and optical scattering, how much light gets bounced around.
They're two key metrics.
We learned that PMMA, an older material, still performs really well optically in many tests. And looking ahead, additive manufacturing, 3D printing, holds just immense potential for creating personalized, maybe even drug-delivering or gradient index lenses.
Huge potential.
But there's still work to do, especially in terms of rigorous, standardized optical testing to make sure these new approaches measure up. We really got a handle on what makes these lenses tick.
We did. And it really does make you pause and think, doesn't it?
Yeah.
About how these advancements, especially this push towards personalized IOLs via 3D printing, could genuinely revolutionize how we treat vision problems.
Yeah.
What other breakthroughs are just around the corner as researchers get better with these materials and techniques? It opens up so many possibilities for truly customized vision.
Definitely leaves you wondering what the future holds. Fantastic stuff. Thanks so much for walking us through all that.
My pleasure.